Okay, so I guess we can start. So last time we talked about naive Bayes. We kind of ran through definitions and finished with some statements about naive Bayes and why it works. So I'm going to now recap and do it a little bit slower. So you will digest this. So this is what we're doing now. So we're talking about Bayesian models in general. And specifically, we started to talk about Bayesian classifiers. So basically, we think about it just as the same predictor or classifier that we talked about earlier in the class. We have a function that maps instances in X to a finite set of values in V. And X is expressed as a collection of features, X1 up to Xn. And given an example, we want to assign it to the most probable value in V. Same game, only that now we have a well-defined notion of what we mean by the most probable. So we basically we want to do the most likely value, so we use Bayes' rule. So the maximum a posteriori V is going to be the argmax over all possible V's of P of Vj, which is one of the labels, Vj, given X. I'm spelling out the X here. And then we're using Bayes' rule, which basically means get rid of the denominator because it's argmax. So Bayes' rule tells us do argmax over this product. And then we said, okay, we can easily estimate this. We cannot easily estimate this. We have to make some assumptions of the distribution. We cannot just expect to count how many times each instance occurs with a specific label. So we have to make some probabilistic assumptions or assumptions on the probability distribution that governs the generation of the data. And the question is which assumption to make. So in this case, we are making the naive Bayes assumption. And the naive Bayes assumption basically tells us this is what you're going to do. We're going to start to decompose this expression, P of X given Vj. We can always write it this way, P of X1 given the rest and Vj times P of the rest and given Vj. You want to make sure that you understand that you can do this and you can do this all the time. We just copy it here and we decompose this one in exactly the same way until we are done. Still, we have the same problem. How do we estimate each one of these components? And this is where the naive Bayes assumption comes in. We are going to say that the feature values are independent given the target values. This way, we can essentially say that P of X1 given a lot of other X's and Vj is just P of Xi given Vj. And the same holds for each one of them. So that's the assumption that we made, and this is how we simplify the classifier to instead of look like this, basically looks like this. Product over all features, P of Xi equal to some value Bi, given that the label is Vj. That's naive Bayes. So we can also think about it in a generative way. Now that we made this assumption, we essentially, equivalently, we said, this is how we generate data here. First of all, we generate the label, the Vi or the Vj. Given that, we generate each one of the Xi's. We generated the label according to the PV, and we generated each one of the Xi's according to P of Xi given Vj. So So now we have an algorithm. Very simple algorithm. We just have to estimate size of V parameters in order to estimate this guy. In fact, I'm not accurate here. What should I say instead of size of V parameter to estimate this? Correct me a little bit. How many parameters do you need in order to know P of V for all values of that V can take? Size V minus 1, because they have to sum up to 1. Okay? So I'm cheating a little bit here. Plus, for each one of these V's, which is size V, n parameters, which is P of xi given it. And there are n xi's. Again, I'm cheating a little bit because given a specific Vj, the sum has to be 1. But that's the number of parameters. And again, what I wanted you to notice is that conceptually it's a very different algorithm than those that we've done before. Because all I did here is I gave you data, and I told you, make the naive Bayes assumption, write down the classifier. That's it. So you can compute the classifier or estimate the parameters of this classifier directly from the data. You don't need to check whether you're consistent with the data. You don't need to change anything based on error you're doing. It's a one-shot computation. Yes?
Can you explain again how you derive the probability of x1, x2, etc. given Vj? Yeah, this one.
So we talked last time, I kind of brought to the top of your head some rules about probability theory. One of them was independence and conditional independence. So specifically here, I'm making the assumption that the feature values are independent given the target value. In particular, that means that P of x1 given x2, let's forget about the rest for a second. P of x1 given x2 and Vj is equal to P of x1 given Vj. Because x1 is independent of x2 given Vj. That's what this sentence means. Okay? And therefore, each one of these components can be written as P of x1 given Vj, P of x2 given Vj, P of x3 given Vj, and so on. So I got to this product. So it's conditional independence given the label.
I was wondering, before that step where we simplify all the terms because they're independent, why were we able to expand that first term to so many products?
That's just product rule. Again, go back to the formulas we talked about last time. I can always take this expression and write it as P of x1 given all the rest times P of the rest. P of A comma B is P of A given B times P of B. Okay? And just replace B by all these guys. Okay? So it's basic product rule, if you want, in probability, which you have to go back and convince yourself that you're fluent in, because everything we're doing basically makes use of this. Okay, so once you're convinced, we got to this classifier. And again, I want to remind you that everything here depends on this notion of conditional independence. So make sure that you understand conditional independence. There are two examples here that I will not go over the details of. One of them is similar to what you've seen in your in the quiz, just to make sure that you understand conditional independence and independence. So go over these two slides. What I want is to run over this example quickly. So you've seen this data, you know it. You use the different algorithm to learn whether you want to play tennis given 4 features. Now we're going to do the same thing with naive Bayes. So let's see, what should we do? So remember the data. what we want is to predict V subscript naive Bayes, and this is what we are doing. So we already know how to estimate parameters. The question is, what parameters do we want to estimate? So here are the parameters one has to estimate. So at the top, these are the priors. The probability of play tennis yes, probability of play tennis no. Essentially go to this table and count how many yeses and how many nos. All right? And then on each side, I'm giving you the probabilities, the conditional probability given the yes, and the conditional probability given the no. So what I have to estimate is the probability that outlook is sunny or overcast or any, given yes and no. 6 numbers, right? 3 values for the feature times 2 labels. And the same thing here. Temperature being humid, mild, cool, given yes, no, 6 numbers, and so on. And again, make sure that you understand that it's not really 6 numbers, because there are dependencies, but you're going to write 6 numbers, right? So given the yes, they're going to sum up to 1, because you have to be either sunny or overcast or rainy, given the yes. And given the no, they also have to sum to 1. So really, there are 2 independent given the yes and 2 independent given the no. So it's really 4 numbers here that are independent. But you will write down 6 numbers. That's clear? Yes?
What if you're missing a data point or you're missing a value?
What do you mean missing?
Like one of your instances doesn't have a temperature.
Let's get to it in 2 slides. Yeah, that's certainly a valid issue, right? So, but independent of the data, that's what you have to estimate, right? So you're concerned that one of them, I've never seen one of the values. I've never seen sunny given no, for example. That's your concern, right? Yeah, so we'll get to it in a second. But that doesn't change what values, what probabilities you have to estimate, right? Okay, so that's what we have to do. And then given a new instance, we're going to compute, this is the instance. We have to make this prediction. Now notice that when we compute the probabilities, we don't know what is the instance. And when we look at the instance, we don't know whether it's going to be yes or no. So we basically have to compute the probability of this instance given a yes, the probability of this instance given a no, and then compare. So that's what we're going to do. So these are the, so I didn't give you all the numbers that you have to compute here. You can do this. And what I'm doing here is on one side, I'm placing all the numbers I need for the yes, and on the other one, all the numbers for the no. So this is always going to be there. These are the priors, that 9 over 14, 5 over 14. And now here, I'm computing sunny given yes, sunny given no. Cool, sunny because this is my example. Cool given yes, cool given no, and so on. So I have these 5 numbers. And what this tells me, look at the product of these 5 numbers and compare them. Now notice that these do not sum to 1. Is that okay? You're not worried? Why? We haven't conditioned them. So really, we just did argmax. So we know that this is proportional to the probability, but it's not the probability because we eliminate the denominator. Now, we don't necessarily have to know the probability, but you can, and here I'm normalizing it. So now the probability of no, which is the winner here, this is the true probability, and if you normalize the same way the probability of yes, you should get 1 minus this. Okay, so that's just a simple run of naive Bayes. I'm sure you're familiar with it. I wanted to do it because you're going to do this more systematically in the problem set that we're going to release today. Now, let's go to your question, or at least my understanding of your question. What if we were asked about outlook being overcast? Okay, so change here the outlook from sunny to overcast. Remember that, and let's go look at the data. Why is this a problem if I'm asking about outlook being overcast? They are all yes. So if you try to compute the probability of overcast given yes, you'll get 1. The probability of overcast given no, you'll get 0. Right? Which means that when you plug this in, when you compute it here and then plug it in here, the probability of, I'm replacing this by overcast, is going to be 0, which means you will never say no. Because the 0 will dominate this product. Was that your question? Okay. Yes?
Well, so does naive Bayes usually use smoothing?
Okay, so that we want to avoid that, right? All we've seen is 14 examples. And in 14 examples, or in fact, in the 5 negative examples, even worse, we've never seen overcast. And does this mean that we want to say, okay, so whenever it's overcast, you have to say yes? We don't want to do this, and this is where we bring up the idea of smoothing. So smoothing is a general technique that allows us to deal with sparsity of data. Every probabilistic method, whenever you want to estimate parameters, you have to smooth them, basically smooth it away from 0. There are many, many ways to do it. And we are going to do it in one specific way here. Now, for naive Bayes, by the way, you can do it in many ways, and it really doesn't matter. As long as you do something to move things away from 0, it's going to work. For more sophisticated probabilistic methods, there could be significant differences in how you smooth, but we're not going to talk about it. So here I just want to remind you, how do we estimate? The probability of word k or xk given a value is the number of, I'm writing it as if it's word in documents, which is what you're going to do in your problem set. The number of times the word appears in documents with label v, divided by the number of documents that have label v. And what we want to do is we want to deal with the case, with 2 cases in fact. One is n is too small, so the estimate is not accurate, or nk is 0, like the overcast case here, and this will dominate the estimate. So the smoothing that we're going to do here, which is called Laplace smoothing, basically works like this. So the probability of xk given v is going to be now, instead of nk over n, we're going to add something to the numerator and something to the denominator. Where in this case, we're thinking about a multi-class classifier case. So nk is the number of occurrences of xk, n is the number of occurrences of the label, m is the number of labels that we have, and p is the prior. So if I'm assuming uniform prior, p is going to be 1 over m. Okay? So in the case of 2 classes, I'm going to assume that I'm adding 1 to the numerator and 2 to the denominator. That's it. So I'm basically pushing things away from 0. If you think a little bit about it, I did 2 things. I pushed things a little bit away from 0, and at the same time, I maintain the probability distribution. You can think about this and see that still things are going to be a probability distribution. Okay, so that's just an example. I instantiated it the way I just said by heart, and that's an important component. Okay, one other comment before we are done with this is in terms of how you do this in practice, is that you will typically not do these estimates in this space. Instead, you're going to work in the log space. Because if you have a lot of features and you multiply a lot of small numbers, probabilities are small numbers, you're going to run into underflow problems. And instead, what you're going to do is you're going to work in the log space. So instead of argmax of this product at the top here, you're going to take log and do argmax of log, which is going to give you this sum. To remind you, this is how log looks like. In this case, it's log base 2. You can take log base 10. It doesn't really matter because, as you remember, the difference the base makes is just a constant factor, so it doesn't matter what you do. But the important thing that you want to recall here is that when you take log of probabilities, which is this area here, between 0 and 1, you get negative numbers. So don't be surprised when you do your homework that the numbers you deal with are actually negative numbers. So you're summing negative numbers. Okay? That's really a technical but important point. Question so far? Yeah.
Why did you choose log as opposed to any other function to operate on this? Just for the mathematical function?
Any monotonically increasing function could do it, right? Because I take argmax, I want to keep taking argmax. It's convenient to take log for numerical reasons. If you have, you can take 7 logs or any other function that will maintain the kind of numerical stability is okay.
But here we do it so that you can change products in the sum.
Well, the key reason is numerical stability, because otherwise, when you have a lot of features, very quickly the product will be 0. Numerically, right? It's not 0, but it will be represented at 0. So that's what we are avoiding. If you have other ways of doing it, and maybe there are other ways, I actually have never thought about it, you can do that. That's the only reason. Okay, so we understand naive Bayes. We can run the algorithm. What you will do in the homework is you will run a few versions of naive Bayes. What I will point to at the end today, it's in the notes, but I'm not going to talk about it. You will discuss it a little bit in the recitation today, is that you can run naive Bayes with respect to many probability distributions. It's really the same algorithm, only that the estimation of the parameters is going to be somewhat different. And you will see this also in the problem set. What I want to do is I want to move to the way I ended up last time to kind of close the circle a little bit with understanding naive Bayes and the relation to discriminative algorithm that we talked about earlier. Question here.
Is there, when you're in the, actually it doesn't matter about log space, is there a way for smoothing the probability of the label as well? Like,
Oh yeah, same thing. You will do exactly the same thing. So essentially all I'm saying is instead of computing the fraction, add something to the numerator and denominator to move it away from 0. You can, in fact, you can try it in your homework. If you just add 1 to the denominator, going to work as well for naive Bayes. You don't really have to be principled and you don't have to be sophisticated. By the way, this Laplace smoothing that I showed here actually has a justification. You can prove that under some assumption, in fact, under the right prior, that's what you get. There is a slide that I did not go over, but it's in the notes, in the lecture notes that shows that. But so this is a well justified way of smoothing. Okay, so naive Bayes. So far, I'm going to run over this quickly because you've seen it and you understand it. We talked about naive Bayes as a method to predict. We didn't talk about it as a method to choose a hypothesis. How did we predict in naive Bayes? I'm talking about the Boolean case. I'm comparing this product for v equals 0 and for v equals 1. And I'm taking the one that is largest. I'm making the prediction according to the product that is larger. This is what we've done in the example before. Equivalently, I can look at the ratio. This is the product I get for 1. In the denominator, the product I get for 0. If the ratio is greater than 1, then I'm going to predict 1. So what I suggested last time is to rewrite this. First of all, I'm just inventing a notation. Whenever I deal with v equal 1, I call these probabilities p's, pi's. Whenever I deal with v equals 0, I call these q's. So I can write this as p of vj being 1 times this product. And notice that when I do this, I don't know whether x is going to be 1 or 0, and therefore I'm writing it this way. So if x is 1, I've written pi, because this one becomes 1. If x is 0, I've written 1 minus pi, because this one becomes 1. Okay? And the same thing for the q's. So what I'm doing now is I'm dividing and multiplying here in the denominator. I'm multiplying by 1 minus pi. Before I had here 1 minus pi to the 1 minus xi, and therefore I got this fraction here, pi over 1 minus I to the xi. If you look at the algebra, it's the same thing. Similarly, I do this in the denominator. I basically multiplied and divided this fraction, this expression, by 1 minus qi. Now, I'm going to take log. Log makes everything sum, so I have the log of this fraction here, plus sum over I, the log of this fraction, 1 minus pi, 1 minus qi. And because I had xi here in the denominator, now I have xi with this coefficient and sum over all i's. Okay? Just algebra. And then I ask you to look at this expression and interpret it. And the interpretation is what? How can you think about this expression? Notice this expression says, when this expression is positive, I'm going to say that the example is positive. I'm going to predict yes on this example. So what is this expression? Yeah, it's a linear sum over the xi's, right? So these are coefficients multiplied by the xi. So essentially what I have here is a linear function with this guy, these two things here on the left as my bias term, and these as the coefficient, the ith coefficient. Okay, so basically that's what we got. We said that in the case of two classes, what we have is this ratio can be written as this linear sum. So essentially what we showed is that the naive Bayes makes its decision using a linear function in the feature space. And we explicitly computed the coefficients. That's why I don't need to do any search or anything as we did before, because once you give me the data and I can estimate these P's and Q's, I can write down the decision. I want to write it in a slightly more interesting way. So if this is the ratio that I care about, and given that I'm in the binary case, and P of V being 1 given X is 1 minus P of V given 0 being X, I can do a little bit of algebra and isolate P of V being 1 given X, and I'm going to get this expression. You can do this algebra yourself, or you can follow what's written here, which is the same algebra. But basically, this is the logistic function that we've seen before. 1 over 1 plus e to the minus dot product. Okay? So naive Bayes is really predicting based on the logistic function. It's equivalent to what I said before, predicted based on a linear function. But it's actually important to us to think about it as the logistic function because of what I'm going to say in a couple of slides down the road. Okay, so really, you already asked the question and we discussed a little bit last time, why does naive Bayes work? Why does it work, especially that you never try it. You never measure consistency. So to me, this is the real explanation of why it works. And to make this a little bit more explicit, recall that learning theory told us, well, measure the error on your training data. If your error on training data is small and you have a low expressivity classifier, it's going to be okay. This is generalization theory. Really here, it seems like we're not doing it, but in practice, we actually do it. Because how do people use naive Bayes? They would take these features, x1 up to xn, and run it, compute the naive Bayes, and check how well they're doing on the training data. If they are not going to do well, they will add features. They will add features which, by the way, will spoil even more the lack of conditional independence among the features. Because if you start with x1 up to xn and add, for example, conjunctions over features, which is a natural thing that we've done in many examples, definitely you will not going to be conditionally independent now. Because you'll have x1 and x2 as a feature, and x2 and x3 as a feature. So basically, based on a methodology or methodological reason, along with this low expressivity that we just show, we are really following the learning theory protocol. We try to learn a hypothesis that is consistent with the data, a linear one. If it's not consistent enough, we increase the feature space. Still, we are using a linear classifier because we are estimating using naive Bayes, and that's why it's going to work for us. So really, the explanation boils down to this. Now, you can still ask the question, in practice, naive Bayes actually works quite well. It's never going to be the best classifier. And I think I explained here why. Let's see. But it's going to be a pretty good classifier. And you can ask, why is that? Why does it even have a chance to be almost consistent with the data, or relatively consistent with the data? And really, the answer is deeper than that. The answer has something to do with properties of product distribution. Right? Naive Bayes is a product distribution. We make prediction based on the product of P of xi given V. And product distributions have this density property. They're close to a lot of distributions. But regardless of that, what you want to take from here as a lesson is that it's really a linear function. And therefore, the intuition that you've gained about low expressivity families of function works here too. Now, here is a property. The last bullet here is actually kind of interesting. We're not going to prove this, but one can construct examples that shows that even though naive Bayes is a linear classifier, not all linear classifiers can be expressed via naive Bayes. Let me make this a little bit more specific. So the way I compute the coefficients for the naive Bayes classifier is as fractions, right? One can give a linear function. For example, you can take linear threshold functions of the type that you played with homework 2, I think. M out of n out of 100, right? So you have 100 features. If 20 of them are important, if any 7 out of them are on, the example is positive. And one can show that some functions in this space you cannot express with naive Bayes. So it's not as expressive. This is just as an example, but basically it's not as expressive as the set of functions that you can learn with perceptron or SVM. Some linear functions cannot be expressed this way. Nevertheless, one can also show that for those functions that naive Bayes can express, it will actually converge to them much faster than other algorithms. So you can take a data set, you can compare naive Bayes with, say, SVM, or the algorithm that we're going to talk about in the next 2 slides, logistic regression, compare them, and what you will see that they will typically outperform naive Bayes, but naive Bayes will converge to whatever it can much, much faster than the other algorithms. Just because the way we compute the estimation. Okay, so that's one part of why does it work. This understanding actually can give us the possibility to answer 2 questions. One, we derive naive Bayes based on probabilistic assumptions. Now, if these probabilistic hypotheses behave like linear classifiers, can we take the old linear classifiers that we did earlier and interpret their output as probabilities? Sometimes you want to do this. For example, you want to do it if your classifier is not your final answer. You don't just want to make predictions, but rather you want to take the output of the classifier, the real valued output of the classifier, and use it later on in other steps. And the answer here is going to be yes. And the second is, if probabilistic hypotheses are actually just like other linear functions, can we train them in similar way? Rather than train them like the naive Bayes that we showed, train them discriminatively. And the answer here is also going to be yes, and we're going to gain some advantages from that. So let me just deal with the first one first. So this was the naive Bayes that we showed. And what I can do is I can take the same logistic function that we showed here and say, okay, now I'm plugging here my favorite linear classifier. F is going to be my favorite linear classifier. I'm going to put these 2 coefficients here, A and B, and I can tune them so that this expression behaves like a probability distribution. Okay? Again, so in naive Bayes we said, well, if you take the function that you've learned, Wx plus b, and you plug it in this logistic function, what you get is the probability of the label is 1. I can do the same thing for any linear classifier that you want. Take your SVM, take your perceptron, plug it in, and what you will have to do is you'll have to tune A and B so that, now you will always get a number between 0 and 1 here, but it does not mean that it behaves like a probability distribution. What you can do is you can tune A and B so that it really behaves like a probability distribution. And a lot of packages are doing that. For example, if you play with LBjava, there is a way to do it and tune it in the right way so that it behaves like a probability distribution. Okay, 2. The more interesting question is 2. So we did naive Bayes. We show that it behaves like a linear function, but as I said, not all linear functions can be achieved using this naive Bayes. And the reason is really the independence assumption that we're making. So what we want to do is we want to generalize it. And the generalization is going to be called logistic regression. So I'm going to take exactly the same expression that we derived using naive Bayes. That is, the probability that the label is plus or minus 1 is going to be 1 plus e to the minus this 1 over this. This is the same expression, the logistic expression that we've derived 2 slides ago. Okay? Now, the way we derived it, this W was a very specific W. We got it by counting, by computing the coefficients. Who said that that's the only way to do it? What if you just take this expression and ask, what is the best W? Think about this as an optimization problem. Here is data. I want to derive an expression that looks like this. Find the best W. So now we are getting to the same domain as in the SVM, for example, where I had an expression, a loss function, and what I asked was, what is the best W given this data? The only difference is that my loss function here is slightly different. But that's it. Other than that, I can just run exactly the same algorithm. And this is really what we're going to do. So we're going to ask this question, solve this optimization problem, get a function, get a classifier that has this expression, and the only thing is that the W that we're going to get is going to be more expressive. Any W that you want can sit there, depending on the data, and therefore it's going to behave better than naive Bayes. Of course, it's going to be more expensive to do, because with naive Bayes, as I showed you, trivial to compute the coefficients. Here, it's an optimization problem. So how are we going to do it? We're going to solve exactly the same thing that we've done before. We're going to look at this expression. Our goal is to find the best WB. And so this is the problem that we're going to solve, right? So we're looking for WB that minimizes the negative log likelihood of this. I'm just writing it here. And again, I'm writing it in the log space because it's the log likelihood. 1 second. And this is my optimization problem. So notice that in the literature, you will sometimes see this algorithm called maximum entropy. Used to be more popular earlier, and this name disappears with time. The reason is that this model can be viewed from the perspective of maximizing entropy, but we don't need to deal with it. Yes?
If we calculate a very exact W, would it be overfitting?
Well, so what I mean by computing the W, what I mean is I'm going to take my data and I'm going to find the W that minimizes the log likelihood of the negative log likelihood of the data, which is the same thing as we did with SVM, right? Of course, you're saying you don't want to really minimize it. You also want to regularize it. And that's what we're going to do, right? So we learned this in the first part of the class, that we don't only want to make sure that the empirical error or the empirical loss is minimized. We want to add something. So this is what we're going to do. We're going to take our loss function here. We're going to add a regularization thing, the same regularization that we learned makes sense earlier. And we're going to add a C parameter here to decide how to best weigh these two components, empirical loss, generalization, and that's it. So notice that it's really the same game as we've done before. The only difference is that the loss function now is driven by the probabilistic model that we we did that we kind of got through the naive Bayes intuition. Again, this is the right side is the empirical loss, the left side is the regularization that addresses your concern. You don't want to just care about empirical loss. Okay, to sort of put everything together, we agreed that with the intuition of naive Bayes, but taking it one step further in how we compute the W, we said let's not compute the W using the probabilistic independence assumption of naive Bayes, but rather do optimization. Find the best W given the data. What we want to do is we want to compute the maximum likelihood of this, or the log likelihood of this. And then we agreed to add regularization terms, and we got this optimization, which is really, which is called logistic regression. Now, again, I want to remind you that we talked about other algorithms. We talked about SVM. This was our L1 SVM, which had the same form with the only difference that here we put hinge loss. We also mentioned L2 SVM, which also has the same form with the exception that we put hinge loss square here. And if you want to look at it graphically, these are the different loss functions. So the red one is the one that we introduced now, the logistic regression. The green one is the SVM. The blue one is the L2 SVM. And you can see that, for example, L1 SVM and logistic regression are very similar, which means that you're running a very, very similar algorithm. You take data, you run your gradient descent algorithm or your favorite optimization algorithm to minimize this loss function plus regularization. And whether you run SVM or you run logistic regression, you'll see that you'll get essentially the same results. And this is why, because the loss function is very, very similar. So we kind of close the circle here. We started with naive Bayes. We finished with logistic regression, which is really the same discriminative function or the same discriminative learning that we talked about earlier in the semester. Very similar to the hinge loss that we talked about with respect to SVM and with respect to perceptron. Yes?
If the loss function for the logistic regression is very similar, then why does the naive Bayes perform a little less?
Because it does not optimize this loss function. For naive Bayes, it looks like this, but we are not doing optimization. We are not trying to minimize as a function of W this function. What we are doing is we believe the assumptions and we compute these W's using the estimation that I showed before for the tennis example, for example, or the way you're going to do in your problem set. You do counting of how many times did you see this feature active in the context of this label, and so on. So it's the same functional form, but the computation of the W is different. Here we are trying to find the best W, minimize this expression over all W's. You see what's written there on the left? I can't point to it for some reason. I don't know where okay, here I am. You see, this is minimize this function over all possible W's. That's what logistic regression is doing. Naive Bayes takes this expression and doesn't care about any minimization, just one-shot computation of the W given the data. Okay, so it's not the same learning algorithm. Therefore, not the same W. Therefore, not the same results. I just used the naive Bayes and the probabilistic intuition as a way to motivate logistic regression. It's really the same functional form, only that we've changed our decision. We said, you know what? I'm not looking for the easy life now. I'm not going to compute W just by looking at the data and do some counting. I'm going to take the same functional form and find the best W that fits it. Okay? Other questions? Okay, so that's naive Bayes. What else you can find in these slides that I'm not going to go over? You will find a couple more examples of naive Bayes. Basically, I think 3 different models, 2 models that I'm presenting in the context of text classification. Here is a set of documents. Decide whether you learn a model, decide whether you like the document, a given document or not. And one of them is actually Gaussian naive Bayes. So the same algorithm, only that the probability distribution underlying the generation of the data is the normal distribution. It brings up a little bit of complication because it's a continuous probability distribution. So this is handled in the slides and also will be handled today and tomorrow in the recitations. Other than that, we're going to move over. Questions? No questions. Okay, so where are we? Here. Okay, so before I start, actually, some administration thing. I typically start the class with this, but I realize that either you're still not awake at the beginning or you're not here at the beginning because you asked the same question on Piazza later. So maybe now it's a better time, you're all awake, it seems. This is the same slide that I had last time or the last 2 times. Exam, April 30th. What is covered? As I said, the focus is going to be on the material since the exam, but there's no way to do it without understanding what we've done before the exam, and hopefully what I just talked about in the last 10 minutes is an illustration of why that is. Everything is connected, so know also what we've done before. That's one. 2 is for the 90 of you that are doing projects, I want to talk to you. I think I talked with about 2/3 of the teams, but not all the teams. So please come and talk to me. If you cannot make my office hours, let me know and we'll schedule some other times. And there will be a poster session on May 7 in the evening. Questions? Okay, so what I want to move on talking about is a new family of algorithms that is called EM. Really nice algorithm, interesting for many reasons. Before we start, I know that you know all this. This is just a reminder that we talked about last time. Basic probabilities. You need to know this and know how to use it. The reason I show it is actually for this slide. Sorry. So the algorithm we're going to start talking about today is called expectation maximization. An expectation is the same expectation that is written here. You need to recall what is an expectation of a random variable. So I'm defining it here. It's basically a weighted average, right? So we have a discrete random variable that takes k values with x1 up to xk with probabilities p1 up to pk. So that's the expectation, the average of the xi's. You knew that. An important property of expectation is linearity. So the expectation of x plus y is the expectation of x plus the expectation of y. If you want to convince yourself, think about averages. And you'll convince yourself that it's linear. Okay, so why do we talk about it? We want to talk about it because really we want to talk about semi-supervised learning. Here's a problem. I'm just kind of motivating it from yet another problem in natural language processing. It's called prepositional phrase attachment. The problem is you have two sentences here. Buy a car with money, buy a car with a steering wheel. If you think about it, the word with that appears in both sentences has a completely different meaning on the left sentence and the right sentence. In one case, it's car with money. Sorry, buy with money. And in the second one, it's car with steering wheel. So one case, the with, on the left side, the with is associated with the verb buy, attached to the verb buy. And in the sentence on your right, the with is attached to the car with a steering wheel. And if you want to understand the sentence at some level, you need to figure it out. I look at the preposition, what is it attached to? So, Boolean prediction. So I want to learn a classifier that looks at a sentence, look at the preposition with in this case, and decide what is it attached to. The verb to the left of it or the noun to the left of it. Okay, problem is clear? It's a hard problem. Partly it's hard because just like almost all interesting problems, it's hard to get a lot of data. You have to know what you're doing in order to annotate the data, and to annotate tens of thousands of examples takes time and it's expensive. So we want to do unsupervised learning, or semi-supervised learning, in fact. There's no such thing, I would claim, as unsupervised learning. But that's another discussion. So we're going to use naive Bayes. What does it mean to use naive Bayes? I have two labels, N and V, here. And the examples are x1 up to xn with one of these labels, N or V. What does it mean to use naive Bayes? It means to do this. This is a reminder of what we've done. So basically I have two columns of numbers. On the left column I have the statistics for n, for nouns, prior, P of n, and then P of xi given n. On the right side I have P of v and P of xi given v. And given an example, I'm going to compute the P of n given x. Should I predict n? Or should I predict v? And I'm going to do it using naive Bayes, which means P of n times all the products, P of xi given n, P of v times all the product, P of xi given v, and I'm going to compare. Everyone agrees with that? That's naive Bayes, right? Nothing sophisticated. Here's an example. I saw 10 examples, and I computed this. So I give you the priors and then the row of the n probabilities and the row of the v probabilities. And here is the new example that I was given. And I can make a prediction, right? So again, I have to compute P of n, and I have to compute P of v. And you will check that I chose the appropriate numbers from the different rows, and everything is fine. So I can make a decision, right? So what will be my decision here? Hopefully n, you agree. Okay. So that's nothing new, right? I learned the classifier, I used 10 examples. Now the question is this. Assume that in addition to the 10 labeled examples, I also have 100 unlabeled examples. It was too expensive to label them, but I have the examples. They are just sentences. What do I do? Yeah.
You could, start labeling the examples by which have the highest probability, and just whichever have the highest probability, add it to the labeled examples and then retrain.
Right. Good solution. So basically I have a model already, right? This is my model. I know how to predict on 1, 0, 0, 0. And therefore, as you say, I know how to predict on each one of the 100 examples. So I'm going to predict on them. And what does it mean to predict? To choose N or V. Once I predicted, I'm going to add them to my training data and train. Yes?
You use for any classifier, right? Not just any.
Yes. Excellent. I can do this for any classifier. I can predict, add this to my training data.
Also, like, how would, like, what would you, like, obviously you can't just predict on the 100 examples and then just train on 110, right? Doesn't there have to be some, like, ratio? Like, how much you're adding? Or, like,
Why? What is your concern?
I feel like your model would become more, like, inaccurate.
Okay, so your concern is that I really had only 10 examples. Probably my model is not so good. Nevertheless, I believe it, annotate the 100 examples and assume that everything is fine, and I treat it as gold label data and train on it. So that's your concern, right?
Yeah.
What should I do then? So let's refine this suggestion. Yes?
Maybe I can weight the 10 examples that are properly labeled more than you on the board.
How do I know?
What do you mean by that?
So how should I weight them? So you're saying some examples you want to believe their labels, and some example you don't want to believe their labels. But how do I know which labels to believe and which label not to believe?
The ones I actually had, I believe.
So the 10 examples I initially had, I'm going to believe, and the new 100 I will not believe. So I'll underweigh them a little bit and then train. Although I have to figure out how to train with example of different weights, but let's assume I know how to do this. So okay, so that's another solution. Other options. Maybe yes, go ahead.
We can generate predictions from using a totally different model, such as SVM or decision trees, and then we just let them like learn from each other.
Okay, so that's actually a good idea too, which I'm not going to use today. I could train another model on my 10 examples. What will that give me?
Then you could also have a label of their own and just ask it to generate labels for some of the examples, and given those output you get, you train the other model based on that and just improve that.
Okay, another suggestion.
We could use naive Bayes to choose the hypothesis if we have another hypothesis.
Okay, you're getting too sophisticated here. Let's stick with the simple model. So the suggestion here is good. I could say, okay, now I have two models trained on these 10 examples, and maybe when they agree, I'm more confident. But in general, that means, one second, is that I could not believe to all the 100. I could believe a subset of the 100. The question is, how do I choose this subset? Yes?
I was just wondering if, like, we have our trained model on 10 examples, and then we predict on unlabeled examples. Is it different than training a model on our 10 labeled examples, like predicting on around 10 and retraining the model, and then like doing that over and over again?
You want to hope that it does, because you want to hope that these 100 examples give you some knowledge, some understanding of the problem.
Yeah, so I guess my solution would be like predict on like a small subset and then retrain the model and keep doing that until you.
How do you choose the small subset? Yes?
Could you look at the x's and then assume that they are generated using some probability distribution, then train on that assumption that you have for each of the x's and then combine them, like in the case of the 100 examples, and then compare those parameters from the probability distributions with what you would get on the 10 examples?
So I already do in some sense, right? So remember that naive Bayes is a generative model, I already assume that these are generated this way. Choose a label. Given a label, choose x1 based on the p of x1 given v. Choose x2 based p of x2 given v. The only issue is that what are these p of xi given v? They are taken from my example here. Now notice here, I want to ask you a question here. So you told me here to predict what? What did I predict on the example 1000? N. Why n? Because it's higher. But what is the probability it's n? What?
It's pretty small. It's 3 over 64, which is kind of small.
No, this is not the probability. This is, you see, I did not normalize. If I were to normalize, what will be the probability of n, and what will be the probability of, you should know, this is a quarter of this, right? Okay, so it's 0.8, 0.2 if you normalize, right? So I'm 80% sure that it's n. What if I have another example that I'm only 60% sure of? And I tell you, you know what, you cannot take all the 100, take just a subset. How would you choose the subset? You'll threshold based on this probability, or something like that, right? So if you talk about a subset, you really have a way to choose a subset. So really, there are multiple ways to play here, but all of them will take into account the fact that I actually have probabilities. It's not only decisions. So for example, option 1 could be, I'm going to make the predictions and believe them. A subset of option 1 would be to take a subset of these, and I have to decide how. And I can do it in multiple ways, right? So I can do, take the probabilities and choose the top 50 examples out of the 100. Based on this probability, I'm labeling. And believe them and retrain. Or I can just choose a threshold. Everything that is above 0.75, I'm taking, believing them. There's one other thing which is a little bit related. I thought that you were going to say this when you talked about weighting. So in fact, the examples here are weighted. So you can say, well, don't think about it as a prediction, but think about it as this example is 0.2 V and 0.8 N. Every example now comes with some fraction N and some fraction V. If example is 0.5, 0.5, it's as if I don't listen to it at all. If example is 0.9, 0.1, I want to listen to it a lot. Now, if you think about the naive Bayes algorithm, I don't need to compute the probabilities from integers, right? I can think about it this way. An n-labeled example is n labeled with probability p of n divided by the sum p of n plus p of v. And it's a v example with probability p of v divided by p of n plus v of v. I can take the fraction and estimate probability this way, right? So estimation in naive Bayes does not necessarily mean add integers, right? It's true that I had, let's say, 8 examples with that said v and n, and 2 examples that said n. But what would happen if it's 6.5 examples that said n and 3.5 that said v? I would also get a probability from that. So that's what I'm going to do. So the most general way to think about it is to think about the fractions and weigh example, believe all the examples, but weigh them fractionally. Okay, so basically we suggested so far several algorithms. use the threshold on the probability, choose example labeled with high confidence, label them N or V, continue. Use fractional examples. Label the example, all the example, with a fraction. P is the weight of N, 1 minus P is the weight of V. And there are many other variations of this. And in both cases, or in all cases, use this iteratively. So this is, as you said, can be used with any other classifiers. The only condition I have is that the classifier will provide a believable confidence in the prediction. Once I have a believable confidence, then I can do it. Go back 15 minutes and think about why I wanted to associate a probability with the output of the classifier. Remember? Here is a reason, or at least one reason. Because I want to be able not just to take a number, the value of the dot product, but rather normalize it in such a way that I can believe the confidence. So once I have this, I can do semi-supervised learning. Now, there are other approaches to semi-supervised learning. A lot of them are similar to what we talked about now. You start with some data, you learn a model, you look at the rest of the data, you annotate all of it, some of it, based on some criterion, and you keep on going. These are all called bootstrapping algorithms. And there's another family of semi-supervised learning, which I call here graph-based algorithms, where the idea is that you place all your examples on some graph with the assumption that similar examples on this graph, say the edges, will have weight that represents similarity between examples. Similar example have similar label. And you'll basically propagate labels. If you know a label of one of the example, you'll propagate it to its neighbors on this graph. I'm not going to talk about this type of semi-supervised learning. What we're going to talk about is we're going to keep on talking about the bootstrap learning algorithm, and I'm going to ask the following example. What if, instead of starting with the 10 examples that I had before, now I'm starting with 0 examples? In what way does it change? Yeah?
I think you'd have to be a lot more reliable, or you'd have to rely a lot more on your priors, and like, you'd have to assume that they're really well chosen, or have some like good reasoning for choosing your priors, because like in this case, that's basically all you have to go off of.
So what would I do? Let's assume I rely on something. But remember, before with the 10 example, what it gave me was it gave me a way to predict on some examples. Yes?
Maybe make certain assumptions, like certain degree of similarity between features would lead to the same prediction.
Okay, but still, the basic thing is I need to be able to assign a label to some examples or to all examples. That's what the 10 labels gave me, right? They gave me the ability to take an example like 1000 and assign a label to it, or assign a label plus confidence to it. That's what I need. Yes?
Yes, I think that for a two-class classification problem, I can assign the first unlabeled example randomly, 0 or 1. They're the same because those following examples are similar to the one. The previous one will be assigned the same thing over.
Okay, so the notion of similar here is a little bit fuzzy because I don't have a notion of similar. What I do have is I have an algorithm. But what we're going to do is we're going to do exactly the same thing. Suggestion? So we're going to do the same thing that we did with 10. We are actually going to run exactly the same algorithm here. Where was it? So we're, what did I want? I want this. So I'm going to run exactly the same algorithm. I'm going to guess prediction on labels on these 10 examples. Now, I resorted to the previous example. I learn a model. I choose one of these algorithms. Maybe I'll choose number 2, use fractional examples. I'm going to use this fractional annotation on the 100 examples and keep on learning. And this algorithm that we're going to talk about next time is actually going to be called an EM algorithm. And under some assumption, it's actually going to be a good algorithm. Of course, it will depend on your first guess. If you made good guess at the beginning, you're going to converge faster. If you will not make good guesses, you will not converge faster or never converge. But the key thing is going to be that this class of algorithms is going to be magically good if you understand your probability distribution. If you make good assumption on the family of probability distribution, it will actually be good and work. So, but the idea is going to be exactly the same. I'm going to guess labels on the first 10 examples and keep on working. And what we'll show is that, well, we'll say at least, not show, that this works under some nice assumptions. Okay, I'm going to stop here. Final questions? Okay, so what you will see in your problem set that will be issued tonight is naive Bayes, a couple of versions, and also in the second part of it, you will also play with this semi-supervised algorithm that we talked about before in the last few minutes. Some of the data is going to be labeled, some will not be labeled, and you'll run this family of algorithms and see what happens. Hi. Hi.
I just wanted to ask you a question. So, as I was doing homework 3, I realized I didn't check my grade for homework 2. And when I tried to check, I realized I didn't submit it on Canvas.
Oh.
I submitted it on the ENIAC, but I completely forgot to submit it on
So you
Canvas.
submitted.
I did submit my files.
So what happened with the PDF?
I submitted the PDF as well.
Oh, you submit all of
I
it
submit
on
everything
Canvas.
on ENIAC, but not on Canvas.
I see.
So I couldn't get a grade.
Okay, so
If
talk
you
to
cross-check
the.
my files, they'll be exactly 100%.
Okay,
the same.
so talk to
So I spoke to the head TA. I spoke to
Andy.
Yeah,
Okay.
I spoke to Andy and he told me to speak to you.
Yes, so we will look at it. We just have to get it.
So should I submit it on Canvas as soon as possible?
No, don't submit it. I want to I want to check if they can do it, if they can access it.
Okay.
If they cannot, then I'll ask you to do it, but don't touch it. So,
I'm sure you have not touched it since.
so drop me an email, and I'll make sure that they look at it. Yeah.
Send you my pen key.
Yeah, up. You want it? Okay. Here. Yeah, just that I remember the case.
Check.
From our data set,
then there will be a limit on the accuracy. For example, if we know A is not like we're trying to predict the G we don't have I'm so annoyed.
Yes.
So there's no pass on that.
Well, you hear you, but you don't
Hello, welcome to Penn. Do you have a laptop or a ringer stick? Laptop? Okay, good.
So we'll get you, so you're in good hands with Paul. Paul will make sure that you're completely set up. Dan Roth, he was right there. You'll be meeting with him afterwards, after the talk, so. Should be nice.
And did they explain how we're recording you?
Yes, and I got her to sign the paper and I did I just tell her what's going on.
Okay.
So,
have a low training accuracy, then we're actually learning a biased model. Always with
Right, but it still does not mean that you will not be able to improve. Because the key assumption that we're going to make is that the same distribution governs, an example also governs the other.
I'll give you a little privacy while you get your act
Be
together.
able to climb up.
Get your thing going here. And that's all set. Yeah, get the slideshow going.
so anyway, but yeah, we've got a little bit to go, so we'll be good. So just, but faculty start coming in, people start coming in.
What happened to it?
Oh, he blanked it
I
out.
blanked out, so I can bring it back. See?
The key assumption is
It looks like you're on the,
Yeah.
we are making an assumption on the distribution. I'll talk about it.
Thanks. I have a question about how we're doing the data processing in our project. So our data, the raw data is in the form, so for 10 predictions, it's winner and winner statistics and loser.
You mean for networks?
oh, perfect.
No, this is just in general for data processing for our project.
Oh, for the project.
Yes. So the question we want to answer is, given two is it bound to, instead of saying winner and loser,
It's a good thing though, you come prepared.
Okay, show your laser.
because if we have
And now, if you could put this on.
You just need to be careful what you're saying, because it's gonna start recording very shortly.
Oh, okay.
So you don't know the name.
It records at 5 after automatically.
Oh, automatically? Okay.
Automatically, if
It also puts your voice up into the ceiling too, so we can hear you.
Okay.
they know to start about 5 after, they'll introduce you and then you start.
Okay.
Okay?
Sounds good.
All right, perfect. All right, guys, I need to rock and roll. I will see you after your talk.
Have a great time.
Thank you. Should I leave this?
One conditional on winner and another one conditional on loser. And now, given new data point, you ask which probability distribution does it belong to? Or you actually ask, what is the likelihood of this belonging to this probability distribution versus what the likelihood it belongs to this? So you compute both and you compare. And that's what we did essentially. Computed all the parameters. Take the famous example that they have here. So on the left side, I had conditional probability distribution given yes, latent. The second one was no. And then we gave me an example. I computed the likelihood of belonging to this, the likelihood of belonging to that, and I compare. So that's one option for you. Right?
let's say if you wanted to use a different model, such as SVM.
In fact, you're doing SVM is kind of doing the same thing. It's doing it together. Right? So you know what are the positive examples. You know what are the negative examples.
Hi. Yeah.
The name is Radhika Mita.
Yeah.
Do you need a...
Yeah, and a clicker.
Okay, so everything was set up?
Yeah.
Let's wait till like 3, a little bit over 3.
Okay.
Not pairs. What we,
Two players.
first pair is 2 players and the second value is 1 label, like 2.
So what if I think about it this way?
You met him this morning, right?
Oh, right, yeah.
Faculty will council, they always see that about.
Rain and snow, sun and cloud. The lights.
It's a new MacBook.
Yeah.
Small, I have a small one too, but it's the
With
older one.
the older one?
Yeah.
Yeah. And the touchpad is nice.
You can touch? Oh yeah, this thing, yeah.
Actually, why, I don't know why it's so, it also shows me the slides here.
Oh, they do? Oh man, that's cool. Touch it there.
Yeah.